Recording now. All right, welcome everybody to this very special TWed. We've got a number of guests here, and we're very glad to have you in-house at Winslow. Normally, our TWed talks are friends of Tedalus that have something to say about ontologies or semantic web or knowledge graphs or these sorts of things, but due to requests that we had within Tedalus, we've got a special guest, Dr. Tom Morgan, who's actually going to talk to us about, give us a very applied introduction to using quantum computing and using the RPI Quantum One computer. Tom has been the chief scientist of first of IDEA and then the FOCI, the Future Computing Institute. Since the inception.
Also the only scientist.
Also, but so Tom and I have known each other for quite a few years, since the creation of IDEA almost 10 years ago. And so I will turn it over to Tom. You welcome questions during the...
Yeah, anytime along the way, especially since this may be fairly new material to some of you. As you see, it's part two. We kind of touched on this. Part one was, at least half of it was kind of a review of Fourier Transform. So I'm going to encapsulate that in the first few slides here. It really is not that difficult a concept. How many of you have a familiarity with the mathematics, or at least the idea of Fourier Transform? So that's about half. That's good. So this is the discrete form of the Fourier Transform integral. And the Fourier Transform integral it's a correlation integral. And that's really all it is about, is it's correlating in general, it's some sort of a time series of numbers. You can think of it as like an acoustical signal or an electrical signal. It varies and goes up and down with time. And what you're doing is correlating that with an exponential. Under the covers, you're really correlating it with cosines and sines. The easier way to think about Fourier transform is to think of the inverse, which is Fourier synthesis. In Fourier synthesis, you take a collection of pure sine and cosine waves and add them all together to create this arbitrary time series. Okay, so Fourier transform is tearing that back apart into the individual sines and cosines. So synthesis builds things up, and the transform tears it back down into its pieces. Okay, and I mean the integral. You have an input vector of length j, and an output vector here. I'm sorry, of length n, and an output vector also of length n. So both the same length. Fast Fourier transform, they're both, and they have to be power of 2. All right, so 2, 4, 8, 16 length. And of course, the summation just replaces the integral here. And here's this is the correlation. We talk about it as the kernel or the phase factor, and we're going to be concerning ourselves almost completely with what's going on in here in the exponent of the exponential, the argument here. If you take that whole thing and essentially blow it up, so what we've done is we've taken those indexes over the summation, or you index across the input and the output. So essentially, you start with you camp out basically on, let me go back, you camp out on some element of the output, and you sum over all the elements of the input, applying this exponential term here based on the particular numeric index of the input and the output. And once you finish with one on the output side, you go to the next one and just repeat across time. Okay. So what you're doing is you can form this sort of a matrix look at it. Here's the input. So it's the first row times all of these to give the first one. The second row times all of these to get the second one, down to the bottom. to get the last one. All right. It's just matrix algebra. And these guys in here, this is the exponential. Okay. This is, I don't even remember what I was trying to talk about here, but yeah, everything in this matrix is used once you pass all of the input to the output side. So this is completely used up. So you need to calculate all of these exponentials in here. And, you know, if you're doing, you know, it's not unusual for a time series to have 1,000 values in it. So if you're computing essentially 1,000,000 sines and cosines to accomplish all of this, that's a lot of heavy computation. All right. So we go to this, and what I've done here is I've taken those J's and K's and put them in that exponential term, and just stripped out the phase part of it. There's so many factors of pi, and this is for an 8 by 8. So this is for 8 inputs generating eight outputs. So it's a small problem, and these are all of those terms in here that you're basically going to have to take sines and cosines of. But you can see right away that there's a huge amount of symmetries here. So this row and this column are the same, and this row and this column are the same. And then you can see, you know, more symmetries across the diagonals, more symmetries in the corners, and then periodicities in different places as well. So there's a lot of repetition. So it turns out for this 8-length one, instead of having 64 that you have to calculate, you really only have a handful. And the bigger it gets, the more economical it gets. So the reality is you only have a handful of these things to calculate. You pre-calculate them, put them in an array, and just reference that array as you're doing all the processing. That's what makes fast Fourier transform fast. Right? It's just, you're just cheating. Instead of just, you know, grunting it out, usually doing every one of these as it comes up, you figure out the ones that you actually need, calculate them, and then you're sitting there waiting. So what we're going to go in here now, this is what we used in the first one. There's an IBM textbook that's easily available. If anybody wants, I can give you the reference to it. And it has a lot of different basic Qiskit code, Python code in it. And you can cut and paste this directly into a Jupyter Notebook on the FOCI Cluster, and just press the buttons and start doing things. It's as easy as that. I mean, it only took me a few minutes to actually run the first thing. In their example, I'm going to get rid of a lot of this junk up here, John. If I X this, will it do anything?
I think you're safe.
Let's move this. Okay. In this IBM example, rather than putting in, you know, you think in terms of what I just showed you. You put in a vector of numbers, and you get another vector of numbers out. The input numbers are generally uniformly sampled time series, so they're just amplitude values. And on the output side, you're getting frequencies. And as you see in the previous stuff, the frequencies can be complex values. Okay. In fact, in order for it to work in certain circumstances, they have to be complex values. What they did in this example is it was a shortcut that they used, and unfortunately, it's a little bit more obscure than if they had just done it the straightforward way. What they did was they took 3 qubits, Q0, 1, and 2 here, and they encoded the binary value of 5. Now, binary 5 is 101, okay? 6 is 110, 4 is 100. So it's just they encoded in here. So here's 1, and in qubits, the initial state of any qubit is 0, okay? And this X gate essentially flips it over so it's a 1. So what they've started with here is these qubits set in the 1, 0, 1 state as 5. And then this is the actual quantum Fourier transform circuit. There's a Hadamard gate and then a phase shift, and then a phase shift between 0 and 2, a phase shift between 1 and 2, then a Hadamard gate and a phase shift between 0 and 1, and then a final Hadamard gate. And because after all of this, the results come out in reverse order, there's a swap, and they just swap the first and the last to put it in correct order.
So could you explain
how you get this?
Well, explain what from the quantum. So this is symbology that's common in quantum world, but a lot of the people in this room have never seen this before. You know, this quantum world type stuff.
Well, here's the thing that I'm still trying to learn how to do, to go from that matrix of phase values to a quantum circuit. How the heck do you actually do that? This is from IBM. Now I can explain what's going on in here. All of these are gates, okay? A lot like Boolean gates that you would see in electrical engineering and current classical computing. And they all do some sort of a rotation, just like any other matrix rotation that you would see. There's a couple of caveats though. First of all, the gates have to be reversible. You've got to get the same, you've got to be able to take the output and run it back through to get the input. And in the real classical computing world, that's not required. In quantum, it's required. Okay. And the other caveat in this here, they have to be unitary, which it's really it's about the structure of the matrix itself. Only certain kinds of structures are allowed. So, and the Hadamard here is used to entangle, if you want to entangle two qubits. And that's what's going to happen here is, because you see, there's only 3 things here, right? But we're putting in one value out of 8. So where do we get the 8 from? We'll see in a second. It's from the entanglement. So you put this in, and this is all being run on the simulator, not on the quantum computer. On the simulator, you can get at stuff a little bit easier, and you don't have to live with a lot of the restrictions of the quantum world. And the only important thing of these are called block spheres, and you can see this is X and Y, and the vertical axis is Z. So all the qubits start out with this arrow pointing straight up to the top. And then the first and the third and the second, I'm sorry, the 0th and the second, they start out with the vector straight down. So you start out straight down, straight up, straight down. After running through the circuit, you end up with these 3 vectors. And these are the states of the qubit. All right. This is what the qubits look like. It's not the results of the Fourier transform. Okay. We'll be getting to that a little bit later.
Can you explain just very briefly why you need a quantum or a qubit circuit, a quantum circuit? Why? How does that?
How does this help illuminate the situation?
Well, what is the role of a circuit in the computer?
Oh, a circuit.
Yeah.
They call it a circuit. It's really just a flow diagram of the operations that are going to be performed.
So essentially, it's programmed. It's how you program.
Right. This is yeah. I mean, this is kind of like a flow chart of a program, as you would think of, in classical computing.
Okay.
Yeah. Okay. So this is some more. We start with this, and I'm going the wrong way. What's the matter with me? So this is their starting point. Now, I have to keep moving this stupid thing around. It's better down here. Since what we're doing is rotations, and especially in the quantum world where everything is reversible, you can apply these in different order, and you can break them apart and put them together. And so in their example, what they did was they took this previous circuit took this previous circuit and they basically boiled everything down in here into consolidated rotations. That's what the P is. These are phase rotations. So you still have all the Hadamard gates because you need them for the entanglement. And you get the same result. All right. My first question was, well, that's fine, but what are they doing here? And I suppose, well, they're taking out the X's and the swap at the end. So what did they do? Is it all bound up in here? Is it all bound up in the rotations? And the answer is yes, and here's why. Okay. So again, here's the original one. Are you seeing my cursor okay?
Oh. Yeah, it's fine. We see you moving around.
Okay. Maybe, can I change it maybe?
Don't worry about it. Don't worry about it. It's fine.
I know there's a way to change it, but so what we did was this is the consolidated one on the previous slide, and all we did was add swap at the end, okay? And and this is what we end up with. And if you compare it to the original, you can see that essentially the first and the last have been exchanged. Big surprise, that's what the swap is supposed to do. So we know how to undo the swap, right? Just exchange qubits 0. We've just exchanged the phase factor for 0 and 2. All right. So we do that and get the original output back. Now, again, we start with that circuit that we just had, and we don't put the swap out here, but we put the two X's at the beginning to figure out what they're doing, okay? So we add the X rotations without the swap, and the result is that, well, the first one is now flipped by 180 degrees, and so is the last one. And the second one stays, and the middle one stays the same, okay? So these X's are flipping 180 degrees. Again, big surprise. That was what they were supposed to do. So what we do, just undo it by basically reflipping 180 degrees. And this is the circuit. These are the phase rotations. What we've done is essentially just taken these two guys and taken a pi over 2 off of them, or I'm sorry, a pi off of them, and we restored the output. Okay. So the next thing is, let's take the final step and combine them together, which is what we did here. We just combine those phase rotations for the two things we did to undo what we added in, the additional things we put in, and yes, indeed, you get the right result. Okay. And then the next step that we did was we said, well, this is 4 pi and this is 5 pi over 2. Can we reduce these to some sort of a minimum thing? So the 4 pi went to 2 pi, and the 5 pi over 2 went to pi over 2. All right, we just subtracted out, 360 rotations. They get you back to where you start, so why even do them? And lo and behold, you still get the correct result. So this is kind of a consolidated set of phase factors. So we've combined them, and this just sort of summarizes what we just went through. This is the original one at the top. The one in the middle is their consolidated one, and here's where we've done our own roll your own type of operations. This is the most compact circuit, all right, but this is the least amount of phase rotation. Actually, it's probably the same as this. And the lesson here is that there are many ways to build these circuits, and there's many combinations that you can put together in all of these phase rotations to get you to the same place. And one of the secrets, as I've been told, because I haven't had too much experience with it yet, is when you're building circuits, is to minimize this kind of stuff as much as possible. Okay, it's the quantum equivalent of performance programming on a classical computer. It's trying to get rid of superfluous stuff. Okay. Now this refers back to the first one. One of the things that they did to verify that original quantum Fourier transform code was they ran it on that 5, the 101, and then they took the output and immediately did the inverse transform and got back the original input, which is what you should get if the code is functioning properly. But How do we know that it actually did the transform correctly? All we know is the code performed correctly frontwards and backwards, but is that the correct code initially to do the transform? You really don't learn anything from their little lesson here. All we did was reverse the phase shifts of the forward.
You created something and
right. So if the forward phase shifts really weren't what you wanted, if you reverse them, you would never know that you didn't get what you needed. So we're going to dive in and prove to ourselves that it is actually the correct set of operations. And we're going to do this initially with classical computing. So this is just Python code that I built for running on my workstation. If you've worked at all with Fourier transforms, especially if you access pre-built transform packages out there, you can very quickly get frustrated because there are multiple ways to do the scaling, and there's multiple opinions about is minus forward in time or backward in time. So the easiest thing to do to sort all this stuff out in your mind is to perform tests with some very, very simple things, because these are extremely easy to remember, and they're known results. So you start with a delta function of size 1 at the 0 location in the input array, and you run it through, and what you get is a flat amplitude spectrum. So all 8 outputs, the amplitude spectrum is 1 and the phase spectrum is 0. Now, what's the amplitude spectrum? Remember, it's complex numbers coming out, real imaginary, cosine minus I sine, okay? So in order to get the amplitude spectrum, you square both of them, add them together, and take the square root. And if you're a Fortran programmer, that's called cabs. You remember cabs, don't you, John?
It's a very long time ago.
Okay, complex absolute.
Yeah,
cabs. But it's just the square root of the sum of the squares. The phase spectrum is the arctangent minus the arctangent, at least in my world, minus the arctangent of the imaginary divided by the real. Okay. And you see the phase spectrum is basically 0. And we'll see here why it is. Here's the input vector, 1 and all zeros. And you can see that all the multiplications end up in 0, because this is the only one, and it's only going to be multiplied times this row here. And then this row is multiplied by 0, and so everything turns out to be 0. So all the results are e to the 0, which is cosine is 1 and the sine is 0. So if the cosine is 1 and the sine is 0, all the spectral amplitudes are 1, and all the phase values are 0, because it's the arctangent of 0 over something, and so that's 0. Okay. So that explains why, and that's why that's so important, because it is very simple to do, and you'll know immediately if there's something going on, because typically what'll end up is this won't be 8. It may be 64 or 1 or something like that. And that just tells you that the scale factor is wrong. Because some of these things, they'll take its length 8 and say, okay, we need to normalize by 8, and they'll do it for you. Others say, oh, it's length 8. They'll do it and they'll hand it back to you. You're on your own to normalize it whatever way you want, okay? So there's tricks like that. Let me see. Yeah, this is the next one. The next test is all ones on the input. So you've got a flat input now, and you can see now they all contribute. So you're going to be using this whole matrix now. Oops, what did I do? Oh, I went too far. So this is all ones. Am I missing one? Oh, okay. I went. Oh. I hit the wheel on the mouse. That's what was confusing me. So this is the first one, and here's the second one. What we've done is we've taken a vector and we put in a 1 in the 6th position. This is the equivalent of that 1, 0, 1 that we've already looked at. So in this one, you see that, well, it's mostly zeros, but in the 6th position here, this column will come into play. Okay, so you are going to be using these exponential factors in here, okay? But everything else is still 0. So you still end up with the same amplitude spectrum, all right? So, no matter these things here, it turns out that sines and cosines are still going to basically add up to 1. And I have the wrong. I didn't notice this before. I have the wrong output spectrum here. What happened? This is.
Got jostle around.
Well, I know what I did. I fooled myself. I changed the order. I was doing these first and then this, and I swapped them just before I did the presentation this morning. So this is the input. Here's the amplitude spectrum, and see the input is in position 6, and now you have a phase spectrum. It's a non-zero phase spectrum, and what that's telling you is that this is because of this time shift. This phase shift here is equivalent to the time shift over in this domain, right? And you can use these numbers to figure out how many samples that it's actually been shifted. Okay. And here's the what's going on with the matrix of phase factors. Okay, so this guy here is the only thing that has any effect, and this column here is used. So things happen in here when you do the arctangent to give you these non-zero values to make that phase spectrum. But as I said, when you sum the sines and cosines of these guys, you still end up back at 1 for the amplitude spectrum. So those are the tests. And here's the third thing that you do. Flat input now, and you get a spike, a single spike or delta function at the first frequency, and no phase spectrum. Okay. And what you see is that the delta function in one domain is the flat function in the other domain. This is the most basic of Fourier transform pairs, okay? You put this in, you get that. You put that in, you get this. And if you shift this back and forth, you're still going to get this, but there's going to be some phase shifting in there to tell you that this thing was not at location 0. Okay. So this is how you test the Fourier transform and understand what you've got. And here's the phase factors. Now all of this comes into play, yet it still comes out okay. And really, this is kind of a tip-off to the kind of things that happen inside the quantum computer, because you look at this and say, all these crazy 7 pi's over 4s and 3 pi's over 2s, and you go through all of that and you end up with something that is like this. Why is that? Superposition. That's what and this is what happens in the entanglement. You get these superpositions. It only happens in certain particular cases, but it's the superposition. So it's a way of saying all of this stuff is hidden in this 0 output phase spectrum. Everything is just canceling out conveniently to produce 0, but it didn't start out as 0. Okay, that's just kind of an aside in there. Shift the delta. We did that. I'm pushing the wrong buttons. I don't have enough light on this. Okay, so now let's get to the equivalent of the output classical computation, and we get this from the output, the final state vector of the quantum computation, and that's what we've done here. And this is statement in the Python code where we initialize that vector. Okay, and this is just the statement. It's qc.initialize. And it does the equivalent of those 2 x's that we had in that first circuit at the very beginning. And here's the output state vector. And you see it's all of the real parts. It's kind of hard to parse this just the way they print it out. But all the real parts are the same number, and all the imaginary parts are 0. So the delta function input is correct. The quantum computer gives us exactly the same result. Flat amplitude spectrum, 0 phase spectrum. The only difference, this is at 0.35 and not at 1, all right? Now, the reason for that is in the quantum world, you put in a vector of numbers like this, you have to have it normalized, which means the sum of the squares of all these values have to be 1. All right. I put in all ones. I put in a 1 and get out a 1. Here you put in a 1 and you get out 0.35 because this is normalized. The sum of these squared all add up to 1. The sum of these squared all add up to 1. Okay. If these were all 1, it would add up to 8. So it's just, again, it's just normalizing by the length of the vectors, what it kind of boils down to. So nothing surprising in the world of Fourier transform. Here's the shifted version. We've now got the 1 in location 6. And again, now we've got complex values that are a little bit more complicated. And what these things actually are is that 6th column in that matrix. And again, you get what you expect. You get the flat output spectrum, and you get exactly the same plot of the phase spectrum. Again, these numbers are different simply because of that normalization. And then you put in, let's see, this is, and here, this one here, we're putting in a flat one, and I had to normalize the input for this one to make sure that all 8 of these added up to squared and added were 1. So you have this square root of 8 in the denominator each time. And so the flat input produces a spike on the output. And I'm showing you the real and the imaginary part here. And the kind of the point in this is we talk a lot about real valued functions. And when you have a real valued function, there's never anything in the imaginary part, of course. So the real part is the same thing as the amplitude spectrum. That only works when you have a real valued function. So here's another thing that we discovered. I went through that exercise of normalizing by hand to put in the square root of it. Is there a question back there?
Yes, I'm not sure I understand the encoding of the input where there's 8 values in 3 qubits. I know 2 to the 3 is 8, but how exactly does that get put into 3 qubits?
Well, it's put in as 101. So the first qubit is rotated to the 1 position, and so is the 0 and 2 are rotated to the 1 position. Yeah, and then during the entanglement is when you end up with this vector of 8 things. Okay, and the 6th one, which is 101, is the one that has a value in it, and that's I'm always missing the so this initialize here has done the same thing. Okay, so if you put, and inside this initialize are those 2 x's basically. In fact, inside the initialize there's 3 x's. It's just that the middle one does 0 rotation. It leaves the qubit where it started. At least that's my surmise, because we don't know, and I haven't found any documentation from IBM or anybody else of what actually happens inside this function. And I'd like to know.
The initialized function?
Yeah. I mean, what is actually going on in there? And my surmise is that it's just doing X operations where one of them is a no-off, basically, it just rotates 0 degrees. And we sort of, in an exercise I went through before, we sort of proved it to ourselves that was what was happening. But again, it's not entirely satisfying to do an impulse response test like this and say, okay, I can't see inside the black box, but based on what I'm getting out, I'm pretty sure I understand what it's doing. I really want to have a look inside the box. Thank you very much, IBM. So we did this, and here's a third or another and final classic thing that we do for testing these things. And this is called the boxcar function or the box function. You see it's 0, 0, 0, and then and I put in 5, okay, 5, 5, 5, and then back down to zeros. All right, so I put in this input vector, and this is the classical computation now. So here's the real and imaginary parts, and here's the amplitude spectrum and the phase spectrum, and you see they're, they're not very symmetrical, they're not very normal looking, certainly more complicated than what we had. Does anybody know what the Fourier transform of a boxcar is? It actually has a closed form mathematical representation. Do you know?
Is it a sink?
It is. It's a sine x over x. In other words, the sine of the argument divided by the argument itself. It's a sinc function, and it looks like this. Okay. It has these little
I
ripples.
remember the shape. I didn't know what it was called.
It's called that. And here's a fun fact for the next time you're at a cocktail party or at a dinner party and you want to entertain the person next to you is, well, first of all, these form a Fourier transform pair, the box and the sinc function. Okay. What do you get? Well, here, what's a triangle function? How can you produce a triangle function? You know? You take a sinc function and convolve it or correlate it with itself. Just take it, multiply a sinc by a sinc, and you get a triangle. Okay? So what's the Fourier transform of a triangle then?
Like,
Oh, it's
like a sinusoidal function or something?
it's what?
Sinusoidal function?
Well, it's like a sinc.
Yeah.
Okay? It's the sinc square. It's the sinc times the sinc.
Oh,
So what this tells you is that convolution in this domain is multiplication in the other domain. So that's your fun fact. If anybody, you want to impress the person next to you, say, you happen to know what the Fourier transform of convolution is. And you
so a sophomore electrical engineer knows.
knows that it's multiplication. But this is a very valuable insight because in the world of Fourier transforms, it's a very general concept. And it's not just columns and vectors and numbers that can be transformed back and forth, but functions themselves also have transform pairs or what, companions, I guess you could call them. So, and time shift has one, and it's you live it, and this is and now what we've done is we've done the same thing now on the quantum computer, and here I've put in the 5s. Say, well, Tom, how could you get away with this? This doesn't normalize to 1. Well, turns out that the normalized function has an extra little feature at the end, and it's called normalize equals. And if you put true, the default is false, okay? And I got an example where it wasn't in the example, and I had no idea that this parameter even existed, and I kept agonizing over, normalizing this stuff by hand. And then I saw another example, and they had normalize out there equals true. Well, that's interesting. So I tried it, and lo and behold, it works. It works just fine. So it saves me a lot of anguish now. And so this is the normalized input. So it's all 0.25s. It's all 1/4 square quarter. You get square them and add them together. You should get 1. Is that right?
Many of them.
1/8, but there's only 4 of these. 4/4 is 1. Yes, I'm sorry. I was saying squared. I guess they must just be summed to 1 then. Anyway, so you get the exact same result. Get the exact. So to this point, the quantum Fourier transform circuit is behaving as we would expect. Yes, indeed, it's a legitimate circuit to do Fourier transform. So again, we've kind of understood the black box, even though we don't know, at least I don't know how to build that circuit from first principles, i.e. that matrix of phase factors. I know how to prove that it works correctly. That's what we've just kind of gone through here. So there's another, it's an instruction that you just put at the end. So you do your quantum computing, and at the end you can just do this. You get the state vector and you can just print it out. It's a Python dictionary, Python list basically. And you can extract, and you see these are the little brackets tips you off that it's a list, and and it's a list of complex valued pairs, They're complex numbers, actually, because there's only the comma just separates each complex number. But in Python, you can just pull these out and access the real and the imaginary parts separately. And in just on the classical side, after the quantum run, you can do the calculations to get the complex spectral magnitude and get do the arctangent and do all of that. And but what I've done here is I just run the classical FFT, and I've printed the classical values versus, these is the same. This is like equals like here. So, and another piece of information that I need to tell you, all of the quantum computer runs have been done with 100 shots. Okay, I don't know how familiar you are, but on the quantum computer, you got to do multiple shots because it kind of averages over them, as I understand it, to mitigate noise. So this is 100 shots, and this is the state vector that you get out. And down here is one single run on the classical computer. You should get exactly the same thing with no noise every time on your classical computer, right? Does anybody see anything suspicious looking back and forth between these two? Is there anything that bothers you about these numbers?
Phase is backwards, or the imaginary part is negative.
Well, you got a -0 here, but I'm not worried about that. All the it's the numbers part. The numbers part. What is?
You're talking about the precision?
Well, I mean, it's floating point computation, so you, at least on this side, you can get all the precision you desire, whether it's real or not. But just look at the first 4 or 5 places to the right of the decimal. They are exactly the same. Would you really expect that on a noisy quantum computer?
No.
Oh, I see your point.
That's what's bothering me right now. When I ran this the other day and saw this, I said, well, this is too good to be true. Especially if you've done 100 shots and sort of average them together, and you're within, a precision of 5 places to the right of the decimal.
So you're saying it should be messier.
Yes, that's exactly it. Why isn't this messier? Why isn't this like 0.71 or 0.69 or something like that? And I don't know the answer to that, and that's kind of the next thing that we've assigned ourselves to find out is we're going to have to go to some real quantum computing people and find out what's going on here. And one of the next thing, in fact, I tried to run this before I got down here, but it never ran.
Why? I have a question. Why is being messier here, like in your opinion, why is being messier here a good thing?
Well, it's not necessarily
that
a good thing. It's supposed to be reality on the quantum computer.
It's supposed to be reality.
That's why you do 100 shots at once, because you're going to get it has to do with the probability measurements that are done on the quantum computer. But I think, if you see, there's no measurement. There's a measurement operation that you can do at the end of your circuit to measure the qubits, and that's what we were seeing in those spheres, those block spheres. That's the result of the measurement, and you only get 3 because you only have 3 qubits. All right. Well, what the measurement does is it collapses the wave function, and that's a probabilistic thing. So you don't necessarily get the same result every time. It's not completely random, but you don't get the same thing every time. That's why you want to do 100 shots, okay? Because it's averaged together. But here we're looking at the state vector, which comes straight out of the quantum computing before many measurements. So the wave function has not been collapsed. So there's 2 questions there's 2 things on my mind. First of all, how do they do that? How do they actually get at it? And again, that's hidden inside this state vector instruction. I have no idea what's going on in there. It's another black box that I just want to lift the lid on.
So are you sure that it's actually not doing like a huge number of iterations?
Well, again, I don't know enough about the quantum mechanics of this, but I suspect what's going on in here is that the quantum circuit actually delivers the exact same final result. It's just the measurement process that introduces the noise. But how do they actually get to the quantum circuit without measuring? And that's the thing that that's my short circuit right now on what's going on in here. So this is kind of where we're at right now. And as you see, there are now more questions at the end of the presentation than there were at the beginning.
So to be clear, when we're looking at that output state vector, is this actually run on the computer? Is this so this is actually
it's run it's immediately after the call to the quantum computer itself.
Okay.
And the quantum computer puts out this thing called the result, which you can print too, and it's huge. There's all sorts of stuff in it. I've looked at it and I've not been able to see anything that looks like the contents of the state vector. So I don't know what's going on in here yet.
Do you have any slides showing the actual submission of the job, that sort of thing?
Well, let me see if I can get on the computer, okay?
Sure.
And just to finish out the thing here.
Oh, yeah.
So
Finish out
in terms of the real world application of Fourier transform, especially for something like filtering, but even if you're just Fourier transforming a whole series of observations, so you have 100 vectors, okay, and you want to transform each one of them. Well, those 100 vectors have been processed, and you have some relative amplitude scaling from one to the other. You just don't want their DCs to be all different, for instance, and things like that. So they're all amplitude balanced beforehand. But the numbers are different. So they're going to each one is going to normalize a little differently. So if you normalize and do the Fourier transform, the transform results are going to be normalized a little bit differently. So with access to the state vector, you know what the normalization was, so you can then undo that. So now you're all balanced equally. Okay. So that's what the first one in here is this renormalization, so that you can rebalance everything, so it's all on an even plane. And then in the transform domain itself, one of the things we'd like to do is filtering. And a very simple filter is to just zero out some of those frequency components. For instance, you have a signal that it's got a nice slowly waving thing, and it's got a bunch of jittery high frequency noise superimposed on top of it. You want to get rid of the noise. Fourier transform that, and your signal is all down on the low frequency side, and your noise is all up on the high frequency side. So you say, oh, you just zero out the high frequency ones and do the inverse transform. Except after you do that zeroing, you now have a non-normalized vector that you have to normalize. So here's a whole other set of normalizations you're going to keep track of. And then you do the inverse transform. So there's an additional thing that you're now going to have to do to rebalance everything. Again, it's kind of an accounting headache. It's not the first time that we've had to do this in the world of computing. I don't know whether John remembers the days of the 16-bit integer vector processors. Oh, yeah. You put in 100 vectors and you get 100 results back. But you also get another vector of bit shifts, because what's happening in there, you get mathematical overflows, and it forces them to bit shift the input a couple of times so that it doesn't overflow. And it keeps track of the bit shifts so that afterwards you can come back and undo them so that everybody's on the same scale. This is analogous to that kind of an exercise. So it's known, all right. And the inverse filtering, I've already gone through this. So these are the next things, and then the big question. I've already mentioned this, but how do we actually build the circuit in the first place? I mean, we were handed this IBM built Fourier Transform circuit. Well, somebody had to sit down and figure out what the actual gates were, and you had to know quantum gates and quantum math in order to get it all to come out right. And that's the other big assignment. What's inside the black boxes, and how do we go from this matrix of phase values? That's what we know about Fourier transform. That's the heart and soul of it. How do we go from that to this circuit of gates? Because that's what quantum circuit design is all about, which is, at least right now, quantum programming. And Qiskit has a whole bunch of functions. And sure, if you don't care, you can just, if you don't want to have to translate your own math into something, you just use something that's pre-computed. And that's fine unless, well, the thing you want to compute doesn't exist in Qiskit, then you've got to design your own circuit, right? So that's the name of that.
So are we to, is the big story that a quantum computer is really a filter?
I thought I went to, okay, here we,
Oh, you're trying to go to the computer now?
yeah. And what what am I'm just spacing out here. I was getting to it from Brave, and
I wouldn't think that, I thought Brave killed JavaScript.
this is, well, I thought I had it all. I don't know why I'm not seeing just the, I can't see the keyboard. RPI. I thought I had just, so this is, John gives you access.
You're not sharing actually this. If you could, you're sharing PowerPoint still, not. Yeah, if you could share, just switch what you're sharing.
Okay, let's see what happened to what happened to my WebEx?
I think WebEx is that.
This?
Yeah, I think that's
No,
what
this is my Outlook. Oh, here it is, right here.
There you go.
And
I think, and that the little sherry do right there.
options.
What's under that one? And then
Cameras. Oh, here it is. Here it is. Stop sharing. Okay. Stop sharing, and now. Still don't understand this.
so what Tom's trying to do is he's through Jupyter Notebooks on what used to be called the IDEA cluster, the FOCI cluster now. We have a virtual environment set up that's got the IBM Qiskit Python packages all set up, so you can actually so you don't have to do all the installations that are required to run Qiskit. And we also have some documentation that talks you through the steps of registering with RPI, so that when you access the IBM quantum computing cloud, you actually end up when you actually submit a computation, you're submitting it to the RPI, to the RPI computer. The way it's kind of very, very loosely speaking, it's sort of like a batch mode kind of a thing. And to make things practical, IBM is managing our quantum computer. So quantum computer sitting in VCC, RPI administration controls who can get on it, but IBM sort of manage the technical aspects of it because it is a quantum computer. It's a rare thing. And
The web address is correct. It's just giving me a bad gateway. It doesn't like something between.
wait, the Jupyter's giving the bad gateway?
Well, yeah. Here I'm clicking on the Jupyter node here, node 2, and this is what I'm getting. It's a bad gateway.
It might be. How about one of the other Jupyters? It might
Oh,
actually.
you're thinking it just might have gone.
I think it's just a node problem today. There was some.
Oh, here we go. Here we go. I got down to number 3.
Okay. You're still not sharing.
Okay, so share.
Yeah, you should be able to share through that.
Here.
There you go.
Okay, and
There you go.
there's
See
that.
if I can control the layout so you can see it. View is on.
So, okay, this is.
Can people see okay?
Can you see this? This is all Python code. Let me make sure I've got the one that I want to show you here.
So he's on the cluster and he's in a Jupyter notebook that he set up, and he's got this virtual environment that we've built selected for his notebook, Qiskit _ environment.
Okay, so this we'll just quickly go through this. These are all the imports that you need, and the blue line tells you the active screen if you're not familiar with Jupyter. So I'm just going to run the cell, and then the next one is some function definitions, which is the swap is a separate function, QFT, and then they built a separate one for only the rotation part of the QFT. And we'll run that so that it's all set. Now here's the setup of the quantum computing. So we tell it 3 qubits and QC equals quantum circuit. This initializes the circuit to 3 qubits. All of them at the 0 state right now. Okay. And now here's our initialize, and this is where we initialize the boxcar. See the 5s there, and here the normalize equals true, and this is telling you qubits 0, 0, 1, 2. Okay, and so this gives you the ability. Say you had 6 qubits, you could do a different initialization. Apparently, I haven't tried it, but apparently that's what you can do. And then here's a state vector statement. So here's the state vector, and we're just pulling out and calling it the same thing. And we're just printing it. It's a simple print statement. And here's the input state vector. All right, 0, 0, 5, 5, 5, 5, 0, 0. All the imaginary parts are 0. All right, and it tells you the dimensions, which 2 by 2 by 2. I don't know what they're telling us there. All right. So the next step here is to build the final circuit. So we put in the quantum Fourier transform, and we put our measurements on. Okay, so that's what's happened here. Here's the initialize. So this box here just replaces the X's that we had at the very, very beginning of the presentation. And then this from here to here is the QFT, quantum Fourier transform. And then these are our measures. We're measuring the qubits in that order.
Probes.
Okay, so let's see, did I run this? No. Okay, so here's the state vector, and then here's and what you were just seeing before was just left over from last time I ran this, so I reran that. Now here's where we run the multiple, I had shots on 100. I'm just leave this just shots equal 1. We'll just see what we get out of it, okay?
What does that mean, shots? The iteration?
That's the number of iterations, basically,
okay.
so far as I know. So this little black dot up here tells you that, okay, you're in the queue. And you just have to wait for it to black dot to turn off.
So you've got the channel set to IBM Quantum, but because you're you with that token, it's going to the RPI.
Right. That's what this token is all about here, this big long A.
That's like an API key.
So here's the back end equals service least busy, and then here's the transpile, and then this is the result. Result equals back end run, 1 shot, transpiled. Okay, so it did it. And
that was actually on the RPI computer.
Yeah, and this is the big results thing. And here's the output state vector at the very bottom: 0, 0, 0.5, 0.5, 0.5, 0.5, 0. That says output state vector. Oh, I'm an idiot.
I
Well,
wouldn't.
no, this is the input that's turned off. That's the input. Yes, print result, print output, state vector. And this is interesting. This is
You ran it with one iteration.
right.
Well, it's 5 o'clock.
It is. Okay. Well, that's told me something here. Let me, just to make sure, just to show you that it actually does work the way I had. Where's your? I think I have to rerun some of this stuff, but
Might have to run from the top.
I have to start here again. And so it's starting to run again. Now here's this code here is just simple Python code for computing and plotting the amplitude and phase spectrum, and also the real.
That's just
This is just pure
Matplotlib.
Right. It's nothing startling.
All right.
So
Did you turn on the light?
watch it for, if you're interested in this kind of stuff in the Fourier transform, and especially how it might be applied to music, there is a end of next week, watch for it in Morning Mail. We've got a visitor from Stanford coming who is doing. It already came out.
Yeah.
That's nice. Yeah. So what's this?
Is that good?
Counts. Well, this is their thing. Where's mine? Oh, well, you idiot, Tom. You have to actually run it in order to get it.
You can't win if you don't play.
Exactly. So here's the real and imaginary output and the amplitude spectrum and the phase spectrum. So this makes me want to go back and rerun the one shot. Anybody wants to stick around for it, you're welcome to.
So can you talk in sort of general terms? I was describing to some of the people here that were early. You're sort of like Don Quixote.
Tilting it
late spring, in search of trying to do a real problem on the quantum computer.
Right. We have one in the industry that I spent many years working in, and that was seismic data processing. And one of the things that they have going on there is they have these enormous input data cubes. We're talking, 10,000 on a side. And they want to circulate through this whole volume doing 50 by 50 by 50 Fourier transforms and doing some operation in an inverse transform. Okay. So they're short transforms, but on a big volume. And this is a perfect setup for the model that we have here with the classical huge computers that we have over in Tech Park, coupled with the quantum computer. So you do the Fourier transform bit on the quantum computer, and you feed back and forth from the data volume on the classical computer. And that's one of the models that the campus has really been looking at. And the next step here is we can prove ourselves we can do something that's of length 50 and which is only 4 qubits. Is that right? 6 qubits. 6 qubits, and then be able to do whatever function that they want to have done in there, and come back out. And then the rest is, well, is it faster and is it, cheaper?
Well, so I guess my question earlier about whether it's we should think of it as a filter. Is it more efficient to do that part of it on the quantum computer?
And the answer is I don't know. We'll find out. And just as an aside, this is the one shot.
Mm-hmm.
It's just fine. So that just kind of adds to the mystery in my mind.
So in your estimation, how many people are using the RPI quantum computer right now?
Josh, I couldn't give you a number, but just based on how busy it gets at times, it seems like there's either a lot of people using it or there's a few people doing pretty good serious stuff on it. But it is getting used fairly heavy. I heard a number tossed around not too long ago, 30% utilization, which I don't know where that came from, but and that's probably true because there's not too much going on at night maybe or on the weekends.
There's a quantum computing like student organization thing, and they
Student club, yeah.
So I believe they're having a meeting right now.
Right, they meet at 5 o'clock on Wednesdays over in DCC, and I've been to a couple of them, and they're doing, well, I don't know whether they're doing this kind of stuff, but it's a lot of self-education. I mean, they're teaching each other how to, understand gates and circuits, and some of the students are pretty advanced, and they've been doing some of their own research type work. But there's almost 400 students in the club. There's something.
How many are in it for the T-shirt, and how many are in it for the work?
Well, apparently close to half of those are freshmen that just got here. So
That's interesting.
a lot of, just anecdotally, I've heard a lot of people mention that, yeah, I came here because of the quantum computer. Or my parents told me that this is a good place to go because I've got a quantum computer. So, it's gotten a lot of attention, and I've gotten a lot of attention from alumni that I know who were asking about it, and alumni in the area who are doing, computational type things. Who, in fact, we've got a couple who attend the users group. It's open to anybody in the RPI community, really. And one of them did a presentation a couple meetings ago. So there's stuff happening, and it's really, there's several components to this. How well can it scale? And the nice thing about Fourier Transform is you don't have to get a lot of qubits to do a serious size problem. I mean, 10 qubits is probably as much as we need right now for the length of Fourier transforms that we do. And we've got, 237 or 137, something? 137. So that's not the issue. The issue is then, okay, how stable is the hardware environment so that we get reliable results? And then the last thing is, well, how much does it actually cost, time-wise and dollar-wise? How much does it cost versus the way we're doing it with classical? Because ultimately, in the commercial world, that's the equation that they have to satisfy.
All righty. Well, let's thank Tom.
Thank you for coming in.
A very atypical TWed talk.
Thank you for coming by. And audiences.
And you're going to be announcing that users group meetings via the Monday morning mail.
They'll be on morning mail. And if anybody is interested, just, John has my email address. Shoot me an email. I'll put you on our list, because we have an email list that goes out a couple times before each meeting. The next one won't be until January. We're not going to do one in December because of finals and things like that.
Righty.